Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I will not show you something in the true sense of preparing about electronics. I will rather show you something that could be useful if you have a pickup and you want to play vinyl discs, and this pickup of yours does not have a pickup dose preamplifier. Sometimes some models of pickups come very empty on the inside. They just take the signal from the dose and send it straight to a connector on the back of the pickup, and well, that's a bit of a problem because it forces you to have a dedicated amplifier with phono input and RIAA curve correction, and well, sometimes we don't have that. On top of that, these pickups typically, when I say that they are empty inside, I really mean that they are mostly an empty wooden box with just a few mechanisms, and that's pretty much it. So these kinds of pickups actually have enough space to hold enough circuitry to have this preamplifier inside of it. So I have such a pickup, an old Tesla NC430. It's not mine, technically speaking. I borrowed it from a good friend of mine, but I get to keep it for a while, and I got permission to do all sorts of modifications on it. What you see now on the screen is the actual pickup without the plastic cover, and with a whole bunch of things that I put on the front panel, because none of those things existed. Now, I would love to show you everything I've done. Sadly, I can't because, well, I have a problem. Among the many things that I did to this pickup was to install headphone amplifier. The problem is this headphone amplifier doesn't work well, and so I cannot show it to you, right? Because if it doesn't work well, it's not worth showing. I've also built three frequency equalizer for this amplifier, and those equalizers do work well, but they kind of come on the package with this headphone amplifier that doesn't work, so I will skip over that. Instead, I will show you the dose preamplifier, which is probably the most important. I mean, no, not probably, it's definitely the most important thing that you need to have in such a pickup, or you might choose to build it externally. It's a good choice as well. I prefer to put it inside, but basically by having a dose preamplifier with RIAA correction embedded on it, you basically get to have a line level signal that you then can connect to pretty much anything that can play music. You can connect it to a mixer, you can connect it to a receiver, or to any stereo amplifier. Really any audio line or audio equipment that receives line input will be able to receive this signal from this pickup. But without this dose preamplifier, you just won't be able to... you won't have line level signal, and that's a problem. You'll have a very, very small signal. So I'm going to show you all sorts of things, and in the end I will put on Patreon all the files related to this project, so you can just download them and build it yourself. So to begin with, let's look a little bit at what signal the pickup dose give us, so that we know with what do we need to work, and therefore how much amplification do we need to have in order to obtain a line level signal in the end. Well, for me, the background noise of this pickup is somewhere around 10 millivolts. This is how having no disc playing gives you this this signal, this basically background noise that is about 10 millivolts. For me it was 13 millivolts in this particular moment. That's peak-to-peak voltage. And well, when you put a disc and you attach the dose to the disc and you let it play, obviously you will get a higher level signal, and that will depend a lot on the disc, on the music that you play, on the kind of music, on the portion inside the song. And you know, many factors will contribute to this level. I had an old Police vinyl disc lying around, and I played it, and I got a roughly 60 something millivolt peak-to-peak signal from that disc. Again, your actual signal might vary depending on all sorts of factors, but this is pretty much the signal that we are getting from our dose, from our pickup dose. And by the way, I say pickup dose because this is how we say it in my language. You might hear it in other places, or you might see it written as a cartridge, phono cartridge, phonograph cartridge, I don't know, something like that. I don't know how you call it in your language, in your country. We call this device a pickup, not a record, not a phonograph record player, but a pickup. And the head that you place on the vinyl disc, and that is responsible for generating the electrical signal, that is called a dose for us. So I'm gonna keep saying pickup dose. Right, so basically we have, let's say, give or take 50 millivolts that we will need to amplify to get it to line level, which is about 1 volt peak, 2 volts peak to peak. Now, theoretically, if you go search it on Wikipedia or on internet in general, you will find two standards, and the consumer standard, which is at minus 10 decibel volt, that's equivalent for 1 volt peak to peak. However, what I've found on the equipment that I have is that for them line level actually means 2 volts peak to peak, so only 1 volt peak, 2 volts peak to peak. I'm a bit confused myself, but anyway, that's where we need to be at, around 2 volts peak to peak from 50 millivolts peak to peak. So yeah, we need quite a bit of amplification. On top of that, we will want to use as low noise equipment as possible. So the circuit that we are trying to build will need to be as low noise as possible. And well, obviously I did a bit of research on the internet, and I found this particular integrated circuit, which nowadays, due to this crappy fabricated semiconductor crisis, it's not so easy to find anymore. It's not impossible, you can still find it, but you're gonna need to either buy it from a very large electronics parts distributor, or to search for it a little bit deeper. LT1115, made by Linear Technology, nowadays Analog Devices. They claim it's the lowest noise operational amplifier available. Well, lowest noise audio operational amplifier available. Because I think I've actually seen even lower noise op-amps that were, I believe, meant for radio frequency applications. But anyway, yeah, it is indeed, if you search a little bit more, you will see that it is indeed the lowest of them all, lowest noise. They say it's typical 0.9 nanovolts per square root hertz, and a maximum of 1.2 nanovolts. That's pretty good. I have to admit, it's pretty good. What I liked about this a lot more is that, well, they give me from the first page of their datasheet straight what I need, exactly what I need. A schematic for a RIAA phonograph preamplifier. And they claim that the deviation from the calculated curve is really small, like within 0.2 decibels, which is super awesome. So, needless to say, this is what a version of this is what I built. I already had some LT1115s bought from about half a year ago, when I was still finding these pretty easily. So this schematic came in very handy. However, I had to change it a little bit, because I couldn't, or I just didn't wanted to use these components. First of all, if you take a look at the resistors, you will see that they have very strange values, like 562 ohms, 17.8 kilo ohms, 499 ohms, 22.6, and so those are a bit strange. Recently somebody told me that in CMD versions you can actually buy these, all of them, with the exact values written here. I personally don't like, and I avoid as much as possible using working with CMD components. I like the so-called through-hole components because they are much easier to work with, and they don't require so much dexterity and precision. And yeah, I personally like, and there are other advantages that I like about through-hole that are not present in CMD components. But anyway, I needed to change this schematic a little bit so that I adapted to use more standardized values, because these are a bit odd. On top of that, they, besides the LT1115, they also use LT1010, which is a buffer. It's a very special, if you search the data sheet and you look inside of it, it's a very special buffer, also made by Linear Technology, which, yeah, I guess it's awesome from all sorts of perspectives. However, it costs just as much as LT1115, or if not more. On top of that, it's sort of like a power amplifier, because it comes in a package similar to power transistors that have a metal plate, so that you can attach it to a radiator. I don't need it to drive low impedance loads, so I won't be drawing a lot of current from this schematic, this circuit. So I obviously would like to use some other buffer or an op-amp as a buffer instead of this LT1115, so that I can cut down on costs, you know, because costs are important for me. The third reason that I needed to change this schematic was that, well, I just couldn't find this 2N4304 field effect transistor, so I had to use a different one. And therefore, I needed to basically make some experiments to see what's the value of this resistor in my case in order to have a 2 milliamp current through here, because they say that you have to have a 2 milliamp. This is a constant current source, by the way, with a FET and a resistor in the source of the FET. Based on the resistor, you get different values of current, and they say that you need to have 2 milliamps. Well, okay, obviously I needed to experiment a little bit with what I had, so I can use a different transistor here. Fourth reason, and probably the last one, is the fact that they used here in this feedback loop, which is a pretty complex filter essentially. They used a pretty big capacitor here, a 2.2 millifarad capacitor, which honestly I don't really see the point. It's a bit too large, too big. I didn't care that much about the size of the final PCB. But a 2.2 millifarad capacitor is just a bit too big, especially considering that if we want to use higher quality capacitors, which they recommend here, we need to avoid using ceramic capacitors. They say we should use high quality film. Well, I did use film capacitors, polypropylene to be more specific. But I used pretty much the cheapest polypropylene capacitors available, because they are still relatively expensive, especially if you want to buy large quantities, like a few tens, you know, 50, maybe even 100 of each. And we have quite a few values of them, different values. So yeah, and the problem with those polypropylene capacitors, at least the ones that I found, was that they are all pretty large, pretty big, especially because they can withstand high voltages, like 100 volts or more. Now, of course, we don't really need such high voltage capacitors in this circuit, but yeah, well, the problem is when we go for the cheapest polypropylene capacitors, they are those relatively high voltage capacitors, and therefore they are relatively large. So yeah, I will show you in the end the PCB. I will explain a little bit what I've done here. In the end, I have a 65 by 70 millimeter PCB, which is not super big, but it's not small either. I mean, 7 centimeters by 7 centimeters, it's enough, you know. And all of this could have been smaller if I would have used ceramic capacitors, but again, in order to have a higher quality music, we need to use higher quality capacitors, which mean more physical space. Anyway, last but not least, what I've changed with my circuit is that I use plus minus 15 volts instead of plus minus 18 volts like they use here, mainly because for me the second op-amp cannot handle plus minus 18. It's just too much. So I wanted to work with plus minus 15. Anyway, this is my point of inspiration, and from this we have this, and I actually have two circuits that are almost identical. I will explain a little bit in a moment the only difference. Ignore the fact that, well, this is written in Romanian. I will explain everything you need to know. Basically, we need to have a differential voltage to supply to these circuits. So we have a plus, ground, and minus, plus minus 15 volts, like I said, and two bypass capacitors of 1 microfarad each is enough. And just like in the circuit that I've shown you a little bit earlier, we have LT1115 as our main amplifier that takes its input signal from basically the signal that comes from the pickup dose. Oh yeah, another reason why I needed to simplify this a little bit is that they provide here a circuit for both moving magnet and moving coil pickup doses, because they don't know what exactly will you be connecting to it. So they made this a bit universal circuit. This is what MM and MC means. Well, they actually explain it here. In my case, I have a moving magnet dose. I know for sure. I don't plan to change it to a moving coil, so I had no reason to, you know, put the switch here and have all this. I could just remove the switch and have some resistors that are fixed here. So yeah. Also, we see here that the input resistor has different values for moving magnet or for moving coil type of doses. Well, in my case, like I said, I have a moving magnet dose, so the input resistor is 47 kilo ohm one, and I can just leave it fixed. Also, there's an input capacitor that apparently is required. I cannot say exactly why, what for, but anyway, they say that you have to take a look in the specifications of your pickup dose in order to see how large this capacitor needs to be. I have an Audio-Technica ATVM95C, if I remember correctly. And I've read in its datasheet you need to have between 100 and 200 picofarads. So I chose 150, which is basically a value in the middle of the two recommended values. Like I said, I used a different FET. For me, it's NT1115. It could be anything else, but I found this transistor to be relatively easy to purchase and not so expensive. I have found that in order to have 2 milliamps of current through it, you need to play around with the value of these resistors. Even if you have multiple of the same transistors, you still need to play around a little bit because each transistor is unique. So, for example, I took two of them, and for one, I needed to put a 1 kilo ohm resistor in its source. For the other, I needed to put a 680 ohm resistor in its source in order to have the same, give or take, 2 milliamps of current, right? If I would have put 1 kilo ohm for both, I would have had a big difference between them. So this is really the only difference between the schematic for one channel versus the other. All the other components are the same. LT1115 gives signal into the non-inverting input of another amplifier. Like I said, in their case, it was an LT1010 buffer. In my case, I didn't want it to spend that much, so I put an NE5534. It's a well-known high quality low noise operational amplifier, also used in various audio projects. It's configured as a buffer, meaning the minus input or the inverting input is connected straight to the output. Its job is to basically, well, be a buffer between LT1115 and the output and the rest of the circuit. And basically we have here from its output all the way back to the minus input of the LT1115, we have a pretty big filter as how do you say it? As a RIAA correction curve. We actually need all of these capacitors and resistors, this configuration, in order to have a different frequency response, in order for this whole circuit to perform the RIAA correction, in the sense of amplifying low frequency signals, allowing at 1 kilohertz signals to be unamplified, and attenuating high frequency signals, because really that's the whole concept of RIAA equalization. You can search it on the internet. I'm not gonna spend time here because it will make the video even longer. So I will show you in a minute what I've done in order to visualize this filter, and yeah, we will shed some light into it and you will understand what it does and why is it needed. Anyhow, the output is passed through a resistor, and at the very end I've put two resistors with a question mark. I did not knew initially how big the signal is going to be here, and therefore I just assumed that I will need to attenuate in order to get to line level. Actually, the signal is good enough, so we can just take it as it is. In my case, I put a jumper instead of resistor 10 here, and I did not connect anything to resistor 22. So that's why you have these two here. And I've left these on the breadboard, on the not the breadboard, sorry, on the PCB board, just in case, I don't know, some of you will want to attenuate the signal for some reason. So now let's take a look a bit at this filter and let's simulate it in order to see what it does, and to compare these values, which are much more humane than to compare them with these values, which are way too weird. First of all, this filter basically has its input on the output of the second op-amp, and the output of the filter is actually the one that's connected to the negative input of the first op-amp. So in order to simulate it, we need to draw it backwards. Otherwise, we won't get a proper frequency response. So this is what I've done in microcap. On the left, you see my circuit with my values. On the right, you see their circuit with their values. I've actually placed them exactly as they are in here. And we will get to simulate both of them. And the reason why I put both of them is to basically play around with my values until they produce a close enough curve relative to their curve with their values. So I'm pretty content with what I've got here. I've got, with blue, I've got my curve. With red, I've got their curve. And yeah, so this is basically what this filter does. This filter attenuates a lot the low frequencies and attenuates less the high frequencies, and has this particular curve. If you search deeper for this RIAA equalization curve, you will see that it's actually a function of 3 or even 4 frequency points, and the whole formula contains some logarithms in there. That's why the curve is actually needs to be, it's not a straight line, you know, it needs to be somewhat curved in 3 points like that. So that's pretty nice. And in order to, so this is the nice thing, whenever you have a curve like this in the feedback of an op amp, you will get this curve mirrored, and you will get it flipped upside down by the op amp, because when this curve is being fed to the negative input or the inverting input of the op amp, the op amp will do exactly the opposite. It will amplify, in this particular case, it will amplify the low frequencies and attenuate the high frequencies. Now, truth be told, it amplifies all frequencies, but because we still need an overall amplification of our signal, but it amplifies low frequencies a lot more than high frequencies. The biggest difference between their values and my values is at around 1 kilohertz, where their value is it gives a 40 plus 40.1 decibel, and my values give a 40.4 decibel, so there's a 0.3 decibel difference, but it's perfectly fine for me. I don't mind, I don't care all that much, because the truth is, we won't listen to music like this as it is according to this curve. We will still need to send that music through a device that has some equalizers in order to further amplify some frequencies that we like. And that's basically when we get to be super subjective about it, because, you know, everyone likes music differently. So yeah, so basically a difference of 0.3 decibel in the RIAA curve for me means absolutely nothing, especially if that difference is only in a small range of frequencies. And after actually creating the circuit on the PCB, I've made a frequency response analysis with an MDO oscilloscope, and these are basically the results with LT1115 and NE5534. Well, basically meaning this circuit here that I present to you, I have pretty much ideal or very close to ideal frequency response, right? We see an about 60 decibel amplification for the low frequencies, about 40 decibel for the middle frequencies at around 1 kilohertz, and about 20 decibels amplification for the high frequencies. And we get to see, so we're looking, by the way, at the blue curve, not the red one. The red one is for phase. We don't really care about phase. We care only about frequency, the amplitude response in frequency. And we see that we have those curves just like in the simulation that I've shown you before. So yeah, we got what we wanted. Now, the nice thing is that you don't really need to use LT1115 and NE5534 or their version of the circuit or anything like that. Really, you can put here any op amps that have high enough input impedance and that are able to work with plus minus 15 volts, you know. And you have to be careful because some op amps actually cannot withstand 30 volts from one rail to another. They are meant to work with only plus minus 12 or something like that. So you need to be careful about the op amps that you place in your circuit, at least if you use this one powered from plus minus 15 volts. Otherwise, of course, feel free to reduce the voltage and perhaps, I don't know, tweak this circuit a little bit more. But the idea is that you can use pretty much any other op amp. And I've even made a test with Micro A741 op amps for both of them. I've made a test just to see, you know, it's the oldest and probably the worst op amp that still exists on the market, but I just tested it anyway, and there are very small differences. Like, I'm going back and forth between LT1115 and Micro A741, and as you can see, the differences are minor, at least in frequency response analysis. Okay, I don't know about the quality of the actual music. Yeah, I'm willing to bet that Micro A741 will sound somewhat worse. But anyway, the point is, it's not impossible for you to create the circuit this way. Okay, so you're not limited to these op amps. You can use any. You can use TL071 or 061 or something else like that. Okay, so I think I have shown you. Oh yeah. So I will give you on my Patreon. I will upload an archive with all of these files so you can easily create the circuit and use it. And now I won't translate them, they are in Romanian. However, you have an english.txt file here, which basically has explanations for all these files. You have an English explanation for all the major files or the important files, so that you know what they are and basically what to do with them. What I would like to show you now, before I end this video, is a little bit about the circuit board. In their documentation, it says I should have a single point board ground, also known as star ground. Well, yeah, okay, it kind of sucks, but I made an effort and I made it, and it's on the left side of the board here. So this is a component placement perspective. Okay, we are seeing the board from top down, and we are taking a look at placing the components. The copper traces that we see here are actually on the other side of the board. So I put the star ground here, and it needs to have quite a lot of spikes, but I overall managed to do it. For the first channel occupies the upper half of the board, the second channel occupies the lower half of the board. With red we have a positive voltage wire that you need to solder and connect it to plus 15 volts. With blue we have two points here. Both of them need to be connected between each other and connected to the minus 15 volt power rail. With red, with green, we have the input here and the output of the first channel, and with orange, we have input here and output here of the second channel. And of course, we have the ground itself, which obviously you need to connect it as well. And when it comes to connecting things, I highly suggest that you use shielded stereo cables. Okay, it's a must to use shielded stereo cable from the pickup dose to the input of the board. But I would recommend you use shielded stereo cables everywhere, including for the output. Even though we have a higher level output, I would still recommend that you use a shielded stereo cable, because you don't need all that much anyway. Also, so for me, this circuit, this preamplifier, is placed in a plastic box that I've 3D printed on the left side of the pickup chassis, at least looked from the bottom, as we look it from the bottom, because it's upside down here. What I recommend that you do is that you also shield this plastic box, and it's very, very easy to do this. You can buy aluminum tape from pretty much any hardware store, and you can just tape several layers of aluminum on the outside of this box, as well as on the inside of the lid of the box, so that the lid makes electrical contact with the rest of the box. And just take one metal wire from the ground, from the ground of the circuit, and connect it to the box itself. And this way you have grounded, you have shielded basically the entire circuit. Of course, you will need to have some holes or some notches for the cables that you will need to pass from the outside to the inside of the circuit, but those are not a problem. What's important is that you know, this box is shielded, so that the circuit inside of the entire preamplifier is shielded. You get maximum quality audio signal if you don't allow any interference, any outside interference to reach the board. So this is pretty much all that there is to it, and if you do it, I guarantee to you that you will get pretty nice quality music from such a pickup, from such a player. I have tested it. I have tested all this work today. I don't have that many vinyl discs, but well, I have two of them that are pretty good, both from technical perspective and also from an artistical perspective. And yeah, I'm very content with what I got here in the end with this circuit. So I can totally recommend this to you. So with that being said, I'm leaving all these files on Patreon, so you can easily replicate this if you need. It's nice to have. It's nice at least to know that such a circuit exists and that it's you know, easily available to you and easy to build. So yeah, that being said, thank you very much for watching this video. If you found it useful or interesting, hit the like button, maybe the subscribe as well. If you would like to come back, I will try to make more videos more often in the near future. Also, if you would like to support my work on Patreon, I would be most grateful to you by helping me buy equipment and components faster. You are helping me learn new things faster, and in turn I will come here and share with you all the things that I've learned, so that I can make your life easier and you don't have to go through everything that I have to go. So thanks a lot for watching, and I'll see you next time. Cheers!